Exercise 9, SolidWorks simulation. What we're going to do is we're going to go ahead and bring up the E9 file. I'm just going to go ahead and copy and paste this onto my desktop so it's a little bit faster than my actual flash drive. Actually, a lot faster. And then from here, I could go ahead and just find the E9 assembly, double click, and it will open up. In this case, on the processor, I'm going to right click on it, and we see the configuration manager at the top. Select FEA featured and hit the green check. That takes all the details out, so it will run quicker, more efficiently. The heatsink one we actually are not going to use in this exercise, so just right click on it and suppress. Do not hide it, make sure it's suppressed or else it doesn't take it out of the equation. Heatsink 2, you could right click and click on the show components tool. We're only going to apply 7 watts to this unit, so let's now go to the simulation tab. Underneath study advisor, select new study. You can see on the left we have static, thermal frequency, so on and so forth. Let's go with thermal and hit the green check mark. Now what we're going to do is we have to set some of the parts up. So for example, the parts, the core processor, I'm going to go hit apply, edit material, and from here it's a variety of materials that microprocessors are made of. The outer casing is what I'm concerned about, that the silver shield that's on there, which might actually be more of an aluminum. And I'm just going to go ahead and select the basic aluminum. I'm unsure of what it actually is. I could look it up, I'm sure, but I'm going to select 1060 alloy and apply and close. Now as far as the heatsink, I'm going to go ahead and right click over here and apply edit material, and I'm going to make this a copper. So I'm going to just go to copper alloys. There's beryllium and different types of options here. I'm just going to go ahead and go with the basic copper. Apply and close. You'll see that it adopts the properties of it. Okay, the next thing we need to do is we're going to go ahead and we need to select the connections between these two. Right now I have this in exploded mode, and it's really pretty neat because you could actually explode the components apart and SolidWorks will still detect when it runs the analysis as if they're touching. So right now I just have it set to explode. And so I'm going to right click on component contacts and click on contact set. And then for the first one I'm going to select the face of the microprocessor. Oops. Okay, I had to click in that little box even though it was selected in blue to select the surface. Then I'm going to click on where this pink stripe is and select underneath the surface of the heatsink. Be aware that I pre-made split face on here, and that's in the very beginning of the manual. It shows how to do that if you want to do that. Okay, and over here for the information, we're going to select distributed and 0.0001 distributed for the kilowatts, and keep it at SI and hit apply. The next item that we have to do is we have to go over here under the thermal loads and right click and select heat power. In the heat power, we're only going to apply 7 watts. As you can tell, this is a very small heatsink, so it's not going to be able to handle much. So we're going to select 7 watts as the output for the microprocessor. If you're ever curious what the output of a microprocessor is, you could actually Google whatever processor you're looking for and essentially find out from a spec sheet what's the output. Okay, and from here, I'm going to go ahead and select this surface where the output is taking place and hit the green check mark. The next item, we're going to go to thermal loads once again, and this time we're going to select convection. And convection is useful for the exterior to see the pathways of the heat as it travels. So from here we go ahead and we could just select all these surfaces on this model. This is where it could be time consuming, and that's why I have a very simplified model. So make sure you don't leave out any surfaces. All the surfaces should be blue with the exception of the contact surface at the very bottom. Once you've selected all the faces, we have to select a convection coefficient. This could vary. Again, you could look it up on the specific material. I'm going to go ahead and put in 25 watts for the convection coefficient for this copper. The bulk ambient temperature, I'm going to go ahead and put in 300 Kelvin, which is approximately 80 degrees Fahrenheit. Go ahead and hit apply. The next thing I'm going to do is I'm going to go ahead and we'll go ahead and run this. We could also actually create the mesh first, and depending upon our detail level, we could set it to a higher level as such. And I'm going to hit apply. Don't set it too high. We don't necessarily need it that high in this case, but we can see the mesh looks pretty good. Let's go ahead and hit run this study. And this could take some time depending upon the complexity of the model. Now here you could see we have the temperature in Kelvin. To change it, there's several ways you could do this. Just one way, it's very easy. Double click on the rainbow that you see here. And on the left hand side, it'll bring up some of the information. Well, first of all, we could change this to floating point versus scientific notation. And hit the green check mark. Now to actually change the temperature to Fahrenheit or Celsius, go ahead and just double click on this little box up here, and that brings up the options on the left. So we could select Fahrenheit and hit the green check. Now we could see in this case the temperature is getting up to as high as 219 degrees Fahrenheit, which is just it's very hot, and so obviously this is not an adequate cooling solution. And we could actually see the surfaces on the model. We are even able to section through and take a look internally, but we could clearly see at the bottom there where we're getting into 200 degrees. It's over 217, even the dark blue. So from there, let's go ahead and take a look at another option. Under results, we could define another plot. So I'm going to go ahead and click on define thermal plot. And instead of temperature, let's look at resultant heat flux. And shows a vector plot. And we'll go ahead and we'll keep it at, we could select BTUs if you'd like. We'll keep it at watts. And let's go ahead and hit the apply button. Now it's kind of hard to see here. First of all, those little green boxes and things, those are the heat power and convection. You could actually hide these. And then to make these bigger, the actual arrows, because if you zoom up, you'll see it's a collection of arrows for the convection. And so if we right click on the resultant heat flux and go to vector plot options, we can now set this up to as high as 1000% the size, and as well as we can select surface only. And then over here, the density we could adjust. But now you should be able to see the convection, what's occurring on the exterior of the model. And so actually some of the great views here are like if you look at the top view, or even if you go to a front view, you can really get a glimpse of what's going on there. Now, let's say we want to fix this and make it more efficient, or actually make it to where it actually works and stays below 180 degrees. That's where we could go in and we could go back to the model tab here. And we should be able to select this model. Actually, if we go and edit the part. So we have to go back to the assembly, and from here, actually, let's go ahead and select that heatsink. We should actually collapse it. So if you right click at the very top here, you have the option to collapse because it was in its exploded state. And now from here we could actually go and edit this. So if we click on it and we go to edit part right here, we should now be able to click on it and grab the little arrows. And let's say we wanted to increase this, make it larger so that it could handle more. Could select that face. We could also select this face and drag this down, make those deeper, those channels. And the more surface area that you add, and the more mass, in theory, it should actually help the cooling solution be more efficient. Let's turn off Edit Component, and now we could go back to Thermal 2, the tab, and let's rerun this study. And so now we could see we went from around 216 degrees to around 140 to nearly 150. Our threshold was supposed to be about 180, so we're well below that. And again, this is a passive heatsink. This is not using any sort of computational fluid dynamics. So we will cover that in future exercises where we actually use the flow simulation software on actually the same microprocessor and heatsink. And in this case, this is just through without any fan or anything like that working. And that concludes this exercise.